Yeah, so let's start.
Okay.
Okay, hello everyone. Welcome to the primary seminar. Today our speaker is Ian and Adelstein. Yeah. So we'll talk about geometry manipulation. That's our speaker.
Thank you. Um, where's like Rafi and do they usually come? I'm gonna go get Rafi.
Yeah, okay.
Okay, so now we can start. Thanks for coming. Let's see. I know some of you, but not everyone. So let me introduce myself a little bit. So I'm Ian Adelstein, faculty in the math department, but I'm also affiliated with Applied Math now. I am DUS of Applied Math together with John Wetlocker. And so we like do a lot of the undergraduate major type stuff. And then some of the grad students I know because we do like the TF assignments and everything like that. But this is the first time that I'm speaking on my research to most of this audience. So I'm excited to tell you about some of the things I think about. Just like as an introduction, so I was trained as a peer mathematician. Got my PhD in Riemannian geometry. I did a postdoc in geometry. And so the first half of the talk, I want to sort of tell you about what I used to think about. So I'll do half this talk on Riemannian geometry, calculus of variations. I'll give a novel result on the shortest closed geodesic. And then the second half of the talk, I'll move into data geometry, and I'll tell you about a recent project I have there. So the data geometry stuff is joint with the Krishnaswamy lab here at Yale. Okay. So to get started, I'm going to talk about the calculus of variations. How many people are familiar with calculus of variations? Okay, some, not all. So it's a way to do calculus on a space of curves. And what we'll see is that it gives a nice relationship between critical points of some energy function, also like take the derivative, set it equal to 0, and geodesics, which are important curves that I study. So here we have a curve, gamma, time interval a to b into your manifold. Usually when you have a vector field along the curve, you guys probably think of like the velocity field, which goes in the direction of the curve. The variational field will actually be orthogonal to the curve. So it'll be orthogonal to the direction of motion. And it's the generator for this family of curves. So I can say this variation h of gamma in the direction of v. So it has the same time parameter. So all these curves are parameterized from time a to time b. And then there's like this infinitesimal variation direction. So it's picking out which curve you are in the variation, this s parameter. And when I set s equal to 0, I get the original curve, and the derivative in the s direction is exactly this variational field v. This is one way that I can sort of take a curve gamma and talk about a family of curves that are all close to gamma. So I'm going to measure the length just by integrating the speed. And implicit when I write down the speed is that I have some Riemannian metric in order to measure the magnitude of the velocity vectors. So that's showing up here. And then I'm just going to say L of S is the length of the S curve in my variation. So I had that one parameter family of curves. S was between minus epsilon and epsilon, so I can choose out and say which curve I'm talking about when I compute the length. And then the definition, we say this central curve gamma is critical if the derivative is 0 at 0. And this needs to be for every variation of the curve. This is the derivative with respect to S here. Let me give the theorem, then I'll say a little bit more. So the theorem is that the geodesics are precisely the critical points of this length functional. So if I have a curve, and it's a critical point for every possible variation of this curve, then it's a geodesic. And the example you should have in mind is just flat Euclidean space. So if I take a straight line in Euclidean space, that's a geodesic, and any variation will necessarily increase the length with fixed endpoints. And so you realize this straight line as not only a critical point, but actually a minimum of the length functional for any variation. It's actually important, though, that these critical points need not be minima. So we'll encounter some geodesics, which are maybe saddle points of the length functional, not truly minimizing the length functional. And the proof of this theorem here is you just write down the first derivative. So you can take the derivative of length, some terms show up, and importantly, this term shows up. This is the acceleration term, right? It's the derivative of the velocity with respect to velocity. And so when you're geodesic, this term disappears. And this is just like an endpoint term, which goes away. What questions do you have here?
Sorry, I really should reiterate this on the Riemannian manifold. I think you mentioned every variation. Can you give like some other examples of variations, such as first variation?
Yeah, so what I mean when I say every variation is, again, let's consider the Euclidean case. And so I can look at, this variation. So there's a variation, but then I can also look at this variation. And I sort of need to look at all variations at once when I define what it means to be critical. So like this is some like weird infinite dimensional space. Like how many variations of this curve are there? Well, it corresponds to how many vector fields there are along the curve. And we'll see in a couple slides, like this is a crazy infinite dimensional manifold.
So should I think of variations as operations on the curve, or?
I mean, you should think of it like this. Like you can think of it as a vector field, like the space of vector fields along the curve. Again, that's like some infinite dimensional space. You can think of it as this picture. So like actually like one parameter family of nearby curves. Like that's what a variation is.
Okay.
And then in order to be critical, the first derivative with respect to the variational direction has to be 0 for every possible variation. You can't really use this definition. Like it's hard to check every the derivative with respect to every variation. But the characterization is really what's important.
So just to confirm, so variations are characterizations of nearby curves by certain functionals.
Sure, yeah, it's a variation of like a one parameter family of curves. Okay, good. Thanks for the question. Okay, so I want to move into closed geodesics. So closed geodesic is just a geodesic which closes back up on itself. You guys are familiar with the great circles in the sphere. Here's actually, you could think of this as a variation about one of these central curves if you want. Here's some closed geodesics, some torus. Again, these are locally length minimizing curves. So this geodesic is going to minimize on some part of its trajectory, but certainly as I go all the way around, there's shorter paths between points on this geodesic. So geodesics are locally length minimizing curves. And then, I want to do the same thing. I want to realize these closed geodesics as critical points of some length functional. And so I'm going to let capital omega be the space of all loops. And again, this is like a crazy big space. So I'm thinking of all maps from the circle into my manifold. Infinite dimensional space of loops. But again, the closed geodesics are the critical points of the length functional on this loop space. So that's how I'm going to realize, I'm going to use calculus. I'm going to like take the derivative of set equal to 0 to realize closed GD6's critical points. I mean, the first question is like, do I get these critical points? And so the first answer, we have to go all the way back to 1898, Hadamard. The shortest curve in each non-trivial homotopy class is a closed GD6. So here I have a torus. This is like the systole, or the shortest topologically non-trivial curve. And this is a closed GD6. And you can actually demonstrate this variationally, because this is a minimum within its homotopy class. And so, you know, when you get a minimal curve, then you know it's a critical point of the length functional. You don't have to check every variation. So here, the topology helps us find these closed GD6. You know, the next question is, okay, what about simply connected manifolds? So the simplest one we want to think about is the two-sphere. And then, you know, on the standard two-sphere, the round two-sphere, there's infinitely many closed GD6, all the great circles. Poincare is thinking about arbitrary two-spheres. So I'll write that like this. This is a topological two-sphere with a arbitrary Riemannian metric, not necessarily the standard one. Maybe it looks like a triaxial ellipsoid, or maybe it looks much weirder than this. But Poincare shows that there's at least one closed GD6 on any Riemannian two-sphere. His proof isn't variational in nature. He's looking at some curvature arguments. But he like has this triaxial ellipsoid in mind, where each of the three coordinate sections are closed GD6. And so he conjectures that there should be at least three closed GD6 on any Riemannian two-sphere. So this is a conjecture due to Poincare. This is not the Poincare conjecture, which is a statement about simply connected three manifolds. But he was thinking about these things, right? And the answer comes in 1929. So this is Listernick and Sherman. They showed there are at least three closed GD6 on any Riemannian two-sphere. So they answer Poincare's conjecture in the affirmative. And their idea here is they study this loop space and this length functional on this loop space. And again, this loop space, you know, it's like it's analogous to the space of all vector fields along a curve. It's a crazy infinite dimensional space. And they're able to show that it has enough topology to admit at least three critical points. And so because the space is so rich and has so much topology, they're able to guarantee themselves enough critical points to prove this conjecture. 1991, Banger and Frank show there's actually infinitely many closed GD6 on any Riemannian two-sphere using similar methods. And then here's an open question. So it's actually unknown if I put an arbitrary metric on the n-sphere, whether or not it admits infinitely many closed GD6. Certainly the standard metric on the n-sphere does, but for an arbitrary metric, it's unknown. There's a lot that is known here. It's known to admit at least one. Any compact manifold admits at least one closed GD6. Okay, but in particular, here's an open question. Okay, so just in order to, okay, that background is interesting. I like thinking about GD6. I like thinking about closed GD6. It's interesting to think about them as critical points of a length functional. I'm going to move into this question of the shortest closed GD6 just for the next, 5-10 minutes or so that I can show you a novel result. Right? Here's something that I've thought about. And so M is my manifold. D is the diameter of my manifold. So diameter is the furthest apart that 2 points can be. It's the maximum of the pairwise distance function. On the unit sphere, the diameter, so that's the distance between the north and south pole. In high school, you'd probably say it's 2, but this is intrinsic diameter. So I'm actually thinking about like the shortest path along the curve. So diameter is pi for the unit round sphere. And then L is going to be the length of the shortest closed GD6. And Gromov asked in 1983, can we, is there some constant which depends only on the dimension such that the length is bounded above by constant times diameter? And okay, just build some intuition. You shouldn't expect a lower bound on the length of the shortest closed GD6. That's because these metrics can be weird. I can get a neck pinch like this. I can make this neck pinch as small as I want. And so the shortest closed GD6 is just bounded away from 0. That's all you can say. Really, again, the question is, can we get an upper bound in terms of diameter on the length of the shortest closed GD6? And again, the topology helps us. So in the non-simply connected case, here the shortest non-contractible closed curve has length. We already knew it was a closed geodesic, but now I can say it has length bounded above by twice the diameter. And the reason is because if I take the shortest non-contractible closed curve and I look at a pair of antipodes, if the length were greater than diameter apart, then there'd be a shortcut. And then that shortcut would contradict the fact that this was the shortest in its family, right? So yeah, easy when the space is not simply connected. So of course, the next question is, well, what about on the two-sphere? And then there's this series of results. So people have been bringing this constant down. So these are all results on the two-sphere. Croak shows 9D, 5D. Nautowski, Rotman, and Savaro show 4D. So they've shown that the length of the shortest curve is bounded above by 4 times the diameter on any Riemannian two-sphere. Okay, this is something I make my class do. Everyone point to your partner, who you're going to talk to. Who's your neighbor? What do you think the bound is? Go.
2.
Point to your neighbor.
Yeah.
Who's
I
talking?
think again, the only ones I got right is yeah. No, that's it. But yes, I don't have those metrics in mind.
Okay, good job, class. Certainly, the reasonable conjecture is twice the diameter. And if you conjecture 2D, really what you're saying is that the round sphere is optimal for the length to diameter ratio, because the round sphere realizes the length equals twice the diameter. And so it'd be nice if the round sphere like optimized the ratio of length to diameter. This result shocked the world in 2009, or the 10 people that read this paper. But they demonstrated metrics on the two-sphere where the length is strictly bigger than twice the diameter. These are existence results, so they, it's like they can prove the existence of such a metric. They actually can't write down the metric, so they don't know how much bigger than twice the diameter these shortest closed curves are, shortest closed geodesics. But yeah, this is kind of like state of the art. And then, so at this point, you should be able to at least understand my theorem statement. So this is joined with Franco Vargas Paete, who is a Gibbs in the math department from a couple years ago. We give ourselves that the metric is positively curved, so we need a little bit extra here. But then we bring the upper bound on the length of the shortest closed geodesic down to 3 times the diameter. And if this were a talk in the math department, I'd spend the rest of the hour proving this for you. And we'd go through and I'd show you exactly how this works. But I do want to talk about some of this more applied math. And so I'm going to wave my hands at the proof and show you just a couple of the key ingredients and how this works.
Quickly, was the lower bound greater than 2D positively curved? Do you know?
Yeah. They're like infinitesimal deformations of the round sphere.
Okay.
And so yes, positively curved. Yeah. They demonstrate a direction in which to deform the round sphere in which they can push length above twice the diameter. Yeah. So in particular, our result applies to their constructions, but their constructions are probably like 2.01 or something. Like, how far can you push this until you break some of the other properties? Okay, so again, I'm going to wave my hands at the proof, but again, topology is going to help us. And so we'll use the topology of S2, and we actually reduce the question of the existence of short closed GD6 to this strange question, the non-existence of minimal theta graphs. Okay, so a theta graph is an example of a geodesic net, which is some sort of like combinatorial analog of a geodesic. Here's an example of a theta graph in a geodesic net. So it's just like an embedded graph on your manifold. And what makes such an object critical is, okay, if it's a critical point of some length functional, and in this case, what's going on is that each of these curves is geodesic. So you see each of these being halves of great circles, and then also you get some balancing condition at all the vertices. So these curves meet at 120, 120, 120. And that's what's going to guarantee that the first derivative of length for this curve is 0. I could write down the first variation of length again, we could see it's 0 for this curve. But the claim is that this is not a minimal theta graph. That's what I mean by that is that there are directions that I can perturb this curve which decrease the total length. So the second variation I can demonstrate is strictly negative. And you can sort of see it. If I just take these two vertices and I pull them towards each other, then this back curve gets longer, but both of the front curves get shorter. And I can decrease the total length of the curve in this way. Okay. So we prove this lemma, which says that these critical or these stationary theta graphs on positively curved two spheres always admit a direction of decrease within the space of nets for the length shortening flow. So like I showed you, like I can, from this stationary point, I can demonstrate a direction of decrease. And if I want to be technical about it, I write down the second variation, and a bunch of these terms disappear. This is just the boundary term, which we can make go to 0. This term will disappear if the variational field is parallel. And so you really just end up with this term, and here's your Riemannian curvature tensor showing up with a negative sign. And so if we have positive curvature, I can just demonstrate variations for you where the second variation is negative. Okay, and so what this affords me is that, and this is the last slide in this hand-wavy proof, I end up running like a curve shortening flow, some negative gradient descent algorithm on my sphere. And I end up wanting to contract my theta graphs down to a point. The way I set it up, there's a topological obstruction to this happening. And either my flow is going to get stuck on a short closed geodesic, which is good, because then I found a short closed geodesic. And its length will be bounded above by 3 times the diameter that comes from the 3 branches of the theta graph. Or my flow will get stuck on a stationary theta graph. And that's also a possible place where my gradient descent will fail. But what I just showed you is that if I get stuck on a stationary theta graph, I have a direction to continue the flow past these stationary points. And so it sort of gets me out of the woods and piece all the topological arguments together. I demonstrate a short closed geodesic. Okay. Yes, so that's the end of the pure math talk. Any questions about that? Yeah.
Okay, so when you said you could, one of the options is you get stuck on a geodesic. So should that mean I should imagine that like all 3 of the curves in the theta graph wind up sitting on the geodesic, or just like 2 of them and one bridging across?
Yeah, so really what's happening is, I won't even draw this one.
Sure.
I'm trying to sweep out each of these 3 faces independently. And so if I start sweeping this one out, maybe I get stuck on a short closed geodesic.
Okay.
Yeah, so like there's lots of places where my curve shortening flow or like my sweep out could fail. But yeah, this is one way to think about it. It's like a face could turn into a closed geodesic. What other questions do you have here? Okay, well then, it's time for the applied math portion of the talk. And so, again, I'll say this is all joint with the Krishnaswamy lab. And I have a slide on, manifold geometry. This is just some basics. We start with the manifold hypothesis. So super high dimensional data often live on or near a much lower dimensional manifold. This kernel function is sort of what allows us to take our high dimensional data and put a graphical structure on it. I think you guys are probably very familiar with this idea. I think there's this 2003 paper by Belkin Niyogi, which is one of the first that's treating high dimensional data in this way, like giving it this graphical structure. This is called Laplacian eigenmaps. And so they project onto the eigen functions of the Laplacian. And then Koifman and Lafon, a few years later, had this diffusion maps paper, where again, they look at this graphical structure, but they run random walks across the graph, and then they project onto the eigenfunctions of the random walk operator. So in what we do, we're following that line of thinking. So we're going to extract geometry via this diffusion operator. And what we hope to be able to do is study the intrinsic distance or volume on our data manifold, the curvature or the geodesics on our data manifold, or maybe even like write down a full Riemannian metric for our data manifold. These are our goals. And I'll say that like over the past 4 or 5 years, we've written papers sort of in all of these directions. And today I'm going to talk about one method we have for writing down a Riemannian metric on an arbitrary data manifold. Okay. So to get into this, I'm going to put up some definitions. I want to introduce a statistical manifold. So a statistical manifold is just a Riemannian manifold where every point is a probability distribution. So my favorite example is the Gaussian family. This is just the family of Gaussian distributions. It's parameterized by mean and standard deviation. And so this is a two-dimensional statistical manifold. Right? For every choice, every parameter pair, I get a normal distribution over the same probability space, the reals. And you'll note that this kind of looks like the upper half plane, right? Because the mean can be any real number and the standard deviation has to be positive. And we'll come back to this upper half plane model in a minute. The example we're actually working with is this idea that any data manifold can be realized as a statistical manifold. So I need to realize each data point as a probability distribution, and I'm just going to use its row of the diffusion operator. So I'm thinking of it as a distribution, like it's random walk, it's transition probability to all the other data points. And so in this way, I can take a data point and turn it into a probability distribution, and therefore I can take a data manifold and think about it as a statistical manifold. And it turns out that anytime you have a statistical manifold, there's a standard Riemannian metric to put on it. It's called the Fisher information metric. So here it is. I'm defining it to you in coordinates. So this is what the ij entry of the metric looks like. And what I'll say about it is, so this is the standard Riemannian metric on statistical manifolds. The distance it induces, so if I use this metric to compute a distance, this is called the Fisher-Rao distance. And the Fisher-Rao distance measures the distinguishability between 2 points, or really between 2 probability distributions in like an inference sense. So let me give you an example. I really love this example. So we're going back to the Gaussian family. And again, remember I said that the parameter space looks like the upper half plane. But now what I've done for you is I've computed the Fisher information metric. So this is the Fisher information metric on the family of Gaussians. And you see it looks hyperbolic in sigma. And so here's just I got this from the internet, a picture of hyperbolic space. But really what this means is, let me fix 2 means. So let's say like mean minus 1/2 and mean positive 1/2. And if the standard deviation is big, so like up here, that means there's a lot of overlap between my 2 distributions, and they're not very distinguishable. And so this hyperbolic metric will give small distance between these 2 distributions. But as I decrease standard deviation, and as you know on the upper half plane, as you go towards y equals 0, or here sigma equals 0, distances, volumes blow up. So if I look at this pair of distributions, which have same difference in mean, they now look like this. Right? The standard deviation is much smaller. These distributions or these points are much more distinguishable. And so the Fisher-Rao distance, the distance computed using this Fisher information metric, will be much larger between this pair of distributions. So yeah, I think this is like a very illuminating example to think about, like, what are we actually computing here? What is this metric? What is this distance measuring? You have questions here? Okay. So I'm spending a little bit of time on this slide. This is our framework for how we're going to compute this Fisher information metric on a data manifold. And so, okay. We have our data. It comes to us presented in some high-dimensional ambient space. That's d-dimensional ambient space. We train a neural net to give us a latent representation of the data. So some like smaller n-dimensional space. So here I just see like one data point being embedded via the neural net. These are its coordinates in d-dimensional space, and then these are its coordinates in n-dimensional space. And the penalty I use for this embedding is I ask that the Euclidean distance in latent space be equal to the Jensen-Shannon distance between the two distributions. Okay, so the notation on this image changes a little bit. So now x of I is a data point, x of j is a data point, so they're not coordinates of a, but here's the embedding of the ith data point, here's the embedding of the jth data point, and the Euclidean distance here, I train my embedding so that it equals, as long as the loss is 0, the Jensen-Shannon divergence between the two probability distributions. Right? So these are the rows of the diffusion operator. And so, okay, I train this neural net. It's differentiable. That means I can compute this Jacobian. So this is a map from d-dimensional space to n-dimensional space. I'll get an n by d Jacobian. This is not the...
Oh, no, yeah, tell us. I'm just trying to imagine what this Jacobian's gonna look like.
This is not the Jacobian that of weights and biases. Like this is not the Jacobian we use to train our neural net. I'm just thinking like here is some map from d space to n space. It's differentiable. Here's its derivative, and the components look like this. So they're the derivatives of these feed coordinates, which remember are the Jensen-Shannon divergences with respect to the inputs, with respect to these this parameter space of my statistical manifold. And what I'm going to convince you of is that the Fisher information metric, I can write down this ij component using, okay, what is this? This is the ith column of my Jacobian dotted with the jth column of my Jacobian. So all of the information I need to write down this Fisher information metric gets stored in this Jacobian, which I have access to because I've trained this differentiable neural net.
So what sort of nonlinear elements are you using in the neural net?
Oh, they're probably ReLUs or something,
Okay.
would be my guess. Yeah.
That's what I was wondering about differentiability.
Let me ask you, your probability, right? You have a diffusion, right? But you have a diffusion, you have the powers of a diffusion, you have diffusion different times. So you have many probability measures at a given point, right? Which one are you using? One step of diffusion?
We're probably fixing some t, right? I mean, here, all I'm seeing is this is a row of the diffusion operator, this is a row of the diffusion operator. How many
But there's
times
no
have...
diffusion operator, it's all the powers of the operator.
Right.
And
How
the
many...
function of that operator, which contains probability.
Yeah. How many times have I powered this? In practice, I'm not sure what we're using, but fix a power. Maybe 4 is what we often use. Maybe 1, just like the standard
Okay,
diffusion metric.
you use one, you have only one operator.
Yeah. So I will we run an experiment in a couple slides that maybe we'll start to get at this. It's interesting, yeah. Okay, so my claim is that like we train this and we have the ability to compute this Fisher information. Let me give you a couple more mathematical details here. This is how I like to think about what's going on. So I think of this framework as a pullback metric. So what is a pullback metric? Well, anytime I have a map between manifolds, which is differentiable or smooth in this case. So phi goes from m to n, it takes this point x to this point phi of x. I can take the derivative of this map, and that's called the push forward, or in this space, it's often called the Jacobian. And what it is it's a linear map between the tangent spaces. So I get this Jacobian, which goes from the tangent space to m at x to the tangent space of n at phi of x. So you sort of see the map between the linear spaces here. Okay, so that's called the push forward. I can push vectors forward using this derivative, this linear map. Let me also define a pullback. So when n has a geometry, what I mean by that is like when n comes equipped with a Riemannian metric, a way to measure inner products between vectors in the tangent space, then I can induce a geometry on m, which comes just from this map. And the way it goes is, okay, here's my pullback metric. This is going to be my new metric on m. I need to say what it does to a pair of vectors x, y in the tangent space here. And so all I do is I push those vectors forward using the Jacobian, and I compute their inner product using the metric on n. And so in this way, geometry on n can induce a geometry on n. This is this pullback metric. Okay, this is like a very simple idea, but very powerful in order to like put geometric structure on a manifold. The caveat is that what geometry do you get here? Well, you just get the geometry of n. And so it's kind of like a disguised version of n's geometry. But we're going to use this. So let me show you where the Fisher information comes from in this like neural net setup that we have. I'm going to pull back the Euclidean metric from the latent space. And the reason is because I've endowed the Euclidean metric with structure, right? I've matched my penalty term was such that the Euclidean distances matched what I want them to be, this Jensen-Shannon divergence. So here I'm pulling back the Euclidean metric from latent space. I'm pulling it back onto the data space, so like the original d-dimensional ambient space. What does this mean? Well, I push forward these two vectors using the Jacobian. This is just another way to write this inner product. And then, this identity goes away so that when I write down the ij component of this pullback metric, it just looks like J transpose J. And that's exactly what we had before, right? That's the ith column of J, Dara with the jth column of J. Okay. So again, like I'm realizing this Fisher information metric as a pullback of the standard Euclidean metric for my latent space. And okay, you compare this with the standard formulation and you see the same ingredients are showing up. The derivative of these log probabilities are actually becoming because we match the Jensen-Shannon divergence, which is a symmetrized scale divergence, and that's where the log probability terms appear. So we get the FIM, and indeed that's like our theoretical result in the paper. This is often how these things get stated, but in the limit, as the number of samples goes to infinity, if our loss converges to 0, then we show that this Fisher information metric that we're realizing as the pullback actually equals the theoretical Fisher information on the statistical manifold. Another way of saying this is just the FIM is an infinitesimal realization of this JS divergence. So that's kind of what got the project going, was like we realized, when we train a neural net to match some distance that we want, maybe it's diffusion maps, or we're matching the diffusion distance, or maybe it's fates, or we're matching this potential distance. If we do this in a differentiable way, then this Jacobian we can write down has the derivatives of these potential differences or these log probabilities with respect to the parameters of the original space. And so we kind of saw the FIM peeking out at us, and then we just had to write it down. Yeah.
What is n here? If your p samples, how big should n be?
This n. So this n is okay. This is the size of my Jacobian. This Jacobian is, yeah. So, my Jacobian, which is going from d-dimensional space to n-dimensional space. This is like my ambient dimension suit, like 20,000 dimension. This is my latent space, whatever you set it up to be, 100 dimension. And so when I take a column of this Jacobian J, it will have length n. Yeah, and so that's this sum here. You should think about it this way. It's just the ijth entry in this product is just the ith column of J done with the jth column of J. And so these columns have size n. Yeah.
But I mean, like, so if you have these samples, then to realize that as this, to realize the Jensen-Shannon divergence as this Euclidean distance, should that be a lower bound, or how much? And it should go with D.
Yeah. So D here is the ambient dimension of your data manifold. So 20,000 or something like this. How many samples do you have? Maybe you have a few thousand samples, a few thousand data points. So my diffusion operator will be sized data by data. Maybe that'll be 1,000 by 1,000. This n I just choose. This is the dimension of my latent space. It can be, in general, it's lower dimensional. Maybe one thing I will mention here, and I'll say again when we get to it, is that this pullback metric, we're pulling back this n by n identity Euclidean metric on the latent space. Here, D is much, much bigger than n. And so we do get a D by D metric on ambient space. This is my FIM. It's going to be rank at most n. So it's super rank efficient. And that'll come up in some of our applications where there's a lot of zero eigenvalues in this FIM. We have to kind of work around that. But yeah, certainly like J transpose J here. So J is M by D. This is D by D, but rank, n, or at most n. Okay, yeah.
You train on all the data?
If
you leave stuff out?
I think we train on all the data. Yeah.
You train, and you just arbitrarily choose an n.
Yeah, I mean, maybe it's a hyperparameter, maybe we optimize it, maybe we
So you
do it a
don't
couple
have a
times.
notion of overfit or something like that. You just because you don't have a test data.
I mean, we train on subsets.
Yeah. And maybe I think of n, I think of n as like it's a latent dimension. I think of it as maybe like the true dimension of my data, right?
Yeah.
But how do I know my true dimension?
So you can do.
Maybe it just needs to be big enough. Like maybe it needs to be bigger than my true dimension so that there's enough space in my latent space to capture the structure. And then
So you basically do like a research on n and just see when your loss is exploding.
sure, yeah. Yeah, I don't have a great sense of how you choose this hyperparameter.
Well, usually you choose it so that you have sort of a bi-Lipschitz map locally from the data to the embedding. That you have not destroyed the distances. So n
Right.
cannot be too small, but it could be D.
Yeah, it could be. Yeah. I think it doesn't really, I mean, you need it to be big enough. But as soon as it's big enough, I don't think there's much harm in having it be bigger.
Yeah.
Because you just need enough dimensions that you're going to be able to capture the structure of the data.
Let me say something else here. Usually when you do this Fisher metric or information geometry metric, the whole point is that it's invariant on the changes of area.
Mhm.
Now, if your data is
Mhm.
described in another coordinate system, it should get the same name.
Mhm.
And that should come up from the formulas here if you did them correctly.
Mhm.
You see, I mean, there's this book by Amari that does a lot of that stuff in the context of information geometry.
Mhm.
But you could do it completely discretely. I mean, you have discrete data, you can do everything the same way. You just replace this covariance, which is the gradient of the log itself, by just looking at covariance of the probability measure. You can actually, there's no reason for you. The parameter theta that you have here could be the actual points.
Mhm.
Right, so your data, you can differentiate, but every point is the center of something, you can differentiate it. The coordinates don't have to be like, anyway.
I mean, in practice, that's what we end up doing. Like, I swept this on the rug, but when we parameterize our data space, we're actually parameterizing it with the points. Yeah, which I find a little unsettling because I like to think of this as my parameterization. Like this is a chart, this is some like lower dimensional representation. But because we're actually defining the metric back in d-dimensional space, we end up parameterizing by the data points. Yeah, like that's how we're parameterizing our metric. Okay. So, okay, we have our FIM. Now we can do geometry. So once you have a metric, you might be interested in volumes. So I can compute the volume of my manifold or regions of my manifold. And then I can also compute lengths now with respect to the metric. So where this speed, the magnitude of this velocity vector is computed with respect to this Fisher information metric. So let me show you what this affords us. And this is kind of like a first experiment that we ran that is kind of off to the side. It's different from the rest of the stuff I'm going to show you. It starts getting at this like diffusion time question. But we're going to realize fate as a two-dimensional statistical manifold. So fate is a dimension reduction, nonlinear dimension reduction visualization algorithm. And there's two important parameters that you choose. The diffusion time, so that's how many times you power your random walk, and then also the bandwidth. So that's like, maybe here it's like how many neighbors you're looking over, or like what the sigma is on your Gaussian kernel. And if I treat those as my two parameters, then for every choice of parameters, I get some fate embedding, or maybe as a subultimate step, I get diffusion operator, like a diffusion matrix. And so that's how I can treat each point of my fate statistical manifold as a probability distribution over the n squared data points, just by like thinking about the diffusion operator as a distribution over the square data points. This image is just to show you that like as you change diffusion time and bandwidth, you get different embeddings. So things look different as you change this. And then this is actually a realization of our statistical manifold. So here are my two parameters. So I'm plotting this in parameter space. And what I've colored by is I've colored by the volume element. So, you know, I run my whole algorithm, I pull back this metric, I get a 2x2 Fisher information metric on this two-dimensional statistical manifold, and I'm coloring by the square root of the determinant of the volume form of the metric. And you see a couple things. First of all, if you look at these level curves, you see they have negative slope. And the reason for this is because bandwidth and diffusion time both work in the same direction, right? As I turn both of these up, I'm looking deeper and deeper across the data. And so if I turn bandwidth up and I want to stay the same, I need to turn diffusion time down. So these work in opposite directions. And that's why we're seeing these level curves with negative slope. And another thing that we see is that, well, there's large regions of the statistical manifold where not much changes as I tune these parameters. The volume element's very small, everything looks very similar. And so if I'm tuning my two hyperparameters over in this region, I'm not going to get much difference. Like all of my embeddings are going to look the same. And so if you want to tune in a place where you're going to see big differences in what the embedding actually looks like, we've identified the region where you want to play around with your parameters. This is kind of like a first interesting application of this Fisher information. And it starts to answer like what diffusion time we're using, things like this. Yeah.
So how does this compare if you use like diffusion distance instead of the distance that you get from the neural net?
Yeah. So I will mention that, but I think what you're saying is, what if we train to match diffusion distance instead of this Jensen-Shannon divergence? Like in our loss function? Maybe I don't understand your question.
Yeah, I mean, maybe it's twofold. First of all, you can train for the diffusion distance, but basically what the network gave you is having a lower dimension
But what happens if you actually take this? I mean, usually the embedding you take is by eigenvectors of the diffusion. And that gives you latent variables and you don't use a neural net for anything, just do it.
That's what.
How does it, that's the question he's asking, how does this compare to the one where you use a neural net to sort of optimize your embedding for the Fisher information?
Yeah, so I'll answer the question. I don't know if I'm answering the exact question, but right. So in our neural net, we're not matching diffusion distance, we're matching this Jensen-Shannon distance. The reason is because then when we pull back the Euclidean metric, we get exactly the Fisher information metric. So that's the term, right? That's the distance we want to match here, so that when we pull this back, we get what we want. You could just as well do, train a neural net to do diffusion maps and match the diffusion distance here in latent space. You could do the same exact thing. You could pull back the Euclidean metric, and what you would get is you get a metric in ambient space whose geometry is that of the diffusion distance. And that would be...
No, it doesn't work. You get, the two of them are the same if you define the graph on the data using the local covariances of the data at one point. So you basically can take a discrete version in the definition of the graph of the Fisher information list. And then when you do the embedding, then it's all the same. In other words, what I'm saying is step 0, which is what is the right distance on the point. Okay, that defines the right diffusion of the point, is to start by basically finding a discrete analog of the Fisher information distance between the densities of the points in the space. So that you can do by just computing Mahalanobis distance locally.
Right.
And when you do that, then you're guaranteed that everything goes all the way and it's independent of coordinates or anything.
So,
Because Mahalanobis is invariant on the changes of variables
okay.
locally. And so you can actually arrange for everything to fit. There's not two different ways of doing it.
And so you're saying like independent of even needing some latent embedding, you just want to do everything,
No,
define
do
everything.
everything using the intrinsic distance, which is, think of intrinsic infinitesimally intrinsic distances being Mahalanobis distance of the.
Yeah, so
So that's invariant on the changes of variable.
Mhm.
Okay. And so you use that, and it's easy to show if you do it normalized correctly that it's the same asymptotically it converges to the Fisher information.
Yeah, so one thing to say here is that one thing this framework affords us is that now we get a metric, because we get Euclidean metric everywhere on latent space, we actually get a metric which is defined on the entire ambient space, not just at the data points. And so, we get this like extensibility.
Because it uses the neural net.
Right, that's what the neural net affords us. And so this will allow us, in some future work that I'll wave my hands at, it'll allow us to do things like generate and so that's like one advantage of using the neural net here. But certainly we could try to just define Fisher information in the data space, but everything is so discrete there. Like you just have finite number of data points. This like gives us the extensibility.
Let's go. Mahalanobis distance is invariant under change of coordinates, but the definition of local isn't. Unless you have like a continuous.
You have to divide, right? I mean, the whole Gaussian that he has there is garbage, right? Unless you normalize it correctly. And you have a metric which is correct, right? So you want to define Mahalanobis, that's okay. You have to decide what is your cluster on every point.
Yes, and
That's okay, that's to be determined. Right?
Yeah.
If you, in any case, he's doing that. I'm saying the basic graph has to be. So how do you define the graph going? That's a good question. I have no idea.
Okay, yeah, there's some chicken and egg here. They're not careful.
Yeah, I mean, the question is not chicken and egg. There's the goal, if you wish. Who is a chicken?
Sure.
Okay, good. Let me just show you a couple more applications. So this one's cool. Okay, here what you're looking at is we have some artificial tree data. So this starts off as like, an affinity graph. That's where we're getting our probability, just transition probabilities through the tree. And you're just looking at like a fate embedding, just like a low dimensional embedding of this tree. And again, what I've colored by here is I've colored by the volume element of my computed Fisher information metric. And okay, the first thing to notice is that, I don't know if you can see, the scale is 10 to the minus 18. So volume is identically 0 everywhere. And the reason for this is, again, this like rank problem, right? Like this is bigger than this. And so this Fisher information metric I'm computing is necessarily rank efficient. Lots of 0 eigenvalues. And so volume is identically 0. But we get around that, we have a hack. So this is the trace of the metric. And trace is not always a great proxy for volume, but what saves us here is that I always think of these as like single part chart parameterizations. I'm not like building up an atlas of charts. Like I'm doing this all in a single chart. And so there, you don't need like any sort of compatibility, and we can talk about trace in this whole parameter space. And so the story to tell then is you see trace is highest at the branching point and then really dies off in the tails. And what I like to think of as happening is that, this is not a metric picture of the data, according to the FIM. The metric picture would really zoom in on this root. And you would really do a lot of work to try to see, okay, where, in which branch do my data points live? Whereas when I get out into the tail of a branch, the metric doesn't need to do as much work. Like everything can just kind of collapse. I already know where I am here. So yeah, I like this story. Here we run it on some real world data. So this is some data set. It has 3 clusters. And so again, you see the 3 clusters and then you see the volume element or the trace being highest, you know, where the metric needs to do the most work. And then the application I like the best is in trying to find shortest paths. So I'm trying to identify geodesics through my data. So here, this is an ambient space. I want a geodesic, and so the simple thing to do is just start with a straight line. So I'm starting with a straight line through ambient space, and then I'm sort of learning a variation. I just like allow my line to deviate from straight, and I compute its length with respect to the Fisher information, and then I just run a gradient descent. And so, like in this way, this is what connects most directly back to the first half of the talk. Like I can think of this variational method, and I'm trying to pick out a minimum in this family of curves around this initial straight line. So we do this. This is just like toy data on the sphere. We see we can sort of match geodesics pretty good. And then here again, a real world data set. So this is embroid body data set. This is single cell sequencing. So super high dimensional, 20,000 dimensional data. This is a 2-dimensional representation of it. And these cells differentiate through time. So you can sort of see the time axis going this way. These cells all start out as some sort of stem cells, and then they differentiate into different types of cells. And these red paths are the Fisher information shortest path. So the geodesics with respect to the Fisher information. And we see, you show this to a biologist and they say, oh yeah, like these are actually the trajectories that the cells follow as they differentiate into the different types of cells, all from like a single base cell. Okay. And then just some future work. One thing we do is like, we've used this framework with an autoencoder as well. So we have a decoder on the back end. And that way we can generate with respect to volume, generate along a geodesic. There's a whole nother paper that we wrote. And then this is a paper that's not ours, but I really like it. They have the same autoencoder framework. And then they actually pull back the metric from the reconstructed space onto the latent space. And they regularize so that the volume element in latent space is uniform. And so here's like a vanilla autoencoder. This is their autoencoder. And this is a latent space representation. So this is kind of like the induced metric from the embedding in some high dimensional ambient space. And I just think they get really nice representations of their data, really nice images. Okay. So that's it. The sphere stuff was joint with Franco. The FIM stuff was joint with Krishnaswamy Lab. Dami was the first author on the neural FIM paper. That's it. Thank you.
Oh, that's very nice, actually. Saying the geodesics in there is coming from the intrinsic metrics is very nice.
Yeah, I like it. I like it a lot. And then like the fact that it actually works.
Yeah, because the intrinsic metrics actually measure the the ability to predict one thing from the other. And so you're looking at the shortest path of prediction.
Mm-hmm. Yeah, and I know like we've talked a couple of times and you've always warned me like this high dimensional data is not necessarily Riemannian. But I think that when our first step is statistical manifold, then like we're guaranteed to have Riemannian structure. And so that kind of gets us around, some of the issues we've talked about previously. All right. Cool. Thank you guys.